Hi, this is Moser with a quick tutorial on resolving vectors into their x and y components. So, after you've watched this video, you should be able to resolve any vector into its x and y components. Well, that seems straightforward enough. You should already know what a vector is and how to use the basic trig functions sine, cosine, and tangent. Let's say that one day you hop in your car and you drive for 17 kilometers in a straight line at exactly 30 degrees north of east. And then someone says to you, "Hey, you, how far east are you?" Well, this is a simple resolving vectors kind of problem. Because in fact, if we look at the vector of your displacement, then really how far east you are is nothing more than your x-axis displacement. To solve this, we're going to need to superimpose a right triangle on this vector, like that, and then we're going to use our handy old trig functions. So you already know that sine for any angle in a right triangle is the ratio of the opposite side divided by the hypotenuse, that cosine is the ratio of adjacent side divided by hypotenuse, and tangent is the ratio of the opposite side to the adjacent side, or opposite divided by adjacent. In this case, since we want to find the x displacement, and we know this angle, we're looking at the adjacent side. So we are going to use our cosine function, and we're going to write an equation that puts the components of this particular triangle into that equation. So in this case, we're going to write it like this. Cosine of theta is equal to the delta x over the total displacement, because our resultant vector is nothing more than the total displacement. Now we can also write r for resultant if you'd prefer. So now we're going to solve for delta x. Well, this is simple. We've multiplied both sides by the resultant to get cosine theta times r equals delta x. Now we can plug in numbers and get an actual value. We get a raw answer of 14.72243, etc. kilometers equals delta x with sig figs. Oh, who wrote this problem? That's terrible. We only have one sig fig in our angle, and yes, your angle does count towards your sig figs. So based on that, we would say that this is 10 kilometers in what direction? Oh yeah, east. That's our delta x displacement. Now, if you had been given a reasonable amount of sig figs like this, then you'd have an answer like 15 kilometers east. But sadly, we are constrained by the terrible problem rating. Oops, sorry about that. Okay, so let's try one more thing. Let's say we have a soccer ball. I think we know a few soccer players. A soccer ball that is kicked with an initial velocity of 25.7 meters per second. That is one heck of a kick, at 38 degrees above the horizon. So the question we want answered is, how fast is this thing traveling upward? In other words, what's its velocity on the y-axis? Note that I've been very careful not to label this as something like delta y, because variables have meaning. Delta y means change in y position, and what we want is the velocity on the y-axis. So we're going to label that as v sub y. Since the quantity that we're interested in is across or opposite the angle that we have, we're going to use the sine function to determine the velocity on the y-axis. Let's set up the sine equation with the variables from this particular triangle. So I've written down sine theta equals velocity on the y divided by velocity. I'm going to rearrange that to solve for velocity on the y. I get sine of theta times velocity equals velocity on the y. Now let's plug in numbers and get an actual value. Sine of 38 times 25.7 meters per second equals velocity on the y. We get a raw value of 15.822499, etc., meters per second, being the velocity on the y-axis. We're limited to 2 sig figs because of our angle. So we find that if this thing were going only straight up, on the y-axis, its velocity is 16 meters per second. So that's its upward velocity. Okay, a couple of cautions. This is about the point where someone usually says, "Oh, Oh, I see. So you always use sine for the y-axis and cosine for the x-axis. No! We have done 2 examples in which that's the case. So just to prove that that's not always the case and it's entirely dependent on the situation at hand, let's do one where that does not work. So here we have the worst drawn peregrine falcon ever. Yeah, it's pretty terrible. Diving off the edge of a building, looking at prey far below. Oh, the humanity. So anyway, the velocity of this peregrine falcon is a shock 68.7 meters per second. What we'd like to know is what is its velocity away from the building? What is its velocity on the x-axis? So again, because the angle that we have is here, and we want the side of this triangle that's opposite that angle, we're going to use the sine function, even though we're talking about the x-axis. So let's set this up. We've got sine of theta equals Vx over V. If we rearrange to solve for V sub x, sine theta times V equals V sub x. Now let's put in some numbers and get actual values. Okay, we get a raw value of 18.93628 meters per second, blah, blah, equals V sub x. Now, the one thing I think I forgot to do on the soccer ball problem, if this is a component of a vector, we of course have to have a direction as well as a magnitude. So let's do this all in one fell swoop. Sig figs, we get 2. That gives us 19 meters per second. What's our direction? Well, this is one where we don't have north, south, east, and west. And remember, those headings are situational. So it depends on the situation you're talking about. In this case, I'd say away from the building seems to work. So 19 meters per second away from the building equals V sub x. Okay, you should work now on the 3A practice problems from Holt Physics Chapter 3. That's these, and you should do all... Oops, wait, hold on, wrong one! Jeez, Moser. Okay, you should do the practice problems from your Holt Physics book 3B. Do them all. It's good practice. Have a good day.